Okay, so yeah. Did you guys try the Fibonacci stuff? Did it work? It worked for you? All of you? It didn't valid outside this. Did you try outside? And it worked for you? Okay, it didn't work for you outside, but it worked for you in. Okay. Did it work for anybody outside? Okay. So yes. So it's actually not going to work outside. I made a mistake yesterday, right? It's only going to work within the range. So that's just the constraint polynomial. There's now another polynomial called so yeah. There's another polynomial called the constraint checking polynomial, right? So that's the one that will now work everywhere. But I want you guys to start implementing multilinear today. So I won't go into too much detail on that now. But then once we're done with multilinear theory, we'll now do like a proper, like using polynomials to prove something. Does that make sense? So now we'll just go back to multilinear. So then the next thing is, did anybody try and design like a dense multilinear polynomial and see how you can do like partial evaluation and stuff? You said it's not possible. Eh? You have to have a what? A passer. Okay, wait. Who attempted it? Huh? Did you attempt? Did you attempt? You saw something that discouraged you. Okay. Rohima, did you attempt? You didn't attempt. Did you attempt? So you guys did attempt. Huh? So what were you saying? Yeah, dance. The first one? Mm-hmm. Mm-hmm. Yes. Index. Uh-huh. Nobody would know. But you can think of a polynomial as rather than A, B, C. You can think of it as first variable, second variable, third variable, right? So anybody that wants to evaluate to say, okay, I want to evaluate the first variable at a certain point. I want to evaluate the second variable at a certain point, or the third variable. So you can get rid of that A, B, C link, right? How you order it, right? Yeah, the order is very important. Yeah. It's actually very important. Because of, sorry, if you just put it anyhow, it's only when you're inserting that you know what the order, right? But when you're done, all you see is just a list of numbers, right? And the coefficient matters. Because if something is 2AC, there's 2 somewhere. And you cannot know that the polynomial is 2AC if you don't know how it was inserted, right? Yes, so you have to pick a standard way. Your polynomial library now. Yeah, for your polynomial library. Okay. Wait, sorry. Yeah.
For me, like, I just said, you can get ABC,
You take the which index? Any position in the array. Okay. Okay. Yeah. Yes. Yeah. 1004. Yeah.
So that way you know that this is
Yeah. Yeah. Okay. So no, dense. It's just an array of coefficients. So you need to put the appropriate coefficient for each. So what I said just now is that but then when you now found that out, did you try and do partial evaluation with that?
I'm not doing it. I just.
Huh? You attempted it, okay. And for now, just express what he said. What the hell is going on here? Alright, so this is what he's saying. He said that you can map the index to combination of zeros and ones, right? So I'm guessing like, let's say you have ABC. A is what? 100. A is 100. I think it's similar to what you guys were saying yesterday about like you rewrite the hypercube to fit that. So you're saying like here now is 0, right? Usually, which will now be like 0, 0, 0. So this is the constant, right? Then here is 1, 0, 0, 1. So is this C? Okay, so this is like const, then this is C, and then you just keep on going like that. Okay. Then did you not figure out how to do partial evaluation? Huh? Okay. Yeah. Oh.
Is this all we have?
Okay, wait. You want to talk about this?
Partial evaluation
Of this, yes.
Yeah, I was thinking the variables for
Yeah.
the ABC. So
Uh-huh.
it's 0, 0, 0. So wherever there is 1 for the last number,
Yeah.
C is active.
Yeah.
So you apply C on it.
Yeah.
So the next one is 0, 1, 0. C is not active.
Yeah.
Next one is 0, 1, 1. C
Yeah.
is active. Apply.
So you're assuming you're partially evaluating C now, right? Okay. So, but then where do you now put the result? So like let's say we had 5BC, right? When you partially evaluate at C, let's say you made C equals 2, right?
Yeah.
So it will be 10B.
Yes.
B is somewhere else. So that 10 needs to move. I don't even get what I mean.
Is it necessary you change the index?
You need to edit something. Let me give a smaller, let's use a 2 variable system, right? 3 variables is too big. So let's say we had like f of a comma b equals to 2a plus b, right? So dense will be what? So this is like 0, 0, 0, 1, 1, 0, 1, 1, right? Based on your rep. So what is this? This const. This is what? B. This is A. And this is AB. So your representation will be no constants, 1 coefficient for B, 2 for A, and none for AB, right? So this is it. So now let's say we wanted to partially evaluate. Oh, this doesn't work because it's too. Sorry. Let's do 2AB. I want something that would collapse down to something else. No, it actually doesn't. It still works because of the constants. Yeah. So now let's say we wanted to partially evaluate at A, right? So A, let's say A is equal to 3, right? When partially evaluate at A equals 3, That's going to be what? 6 plus b. So when you represent this, the 6 is going to be here. 6 is going to be at the constant location. 1 is still going to be at b, but the rest of them are going to be at 0. Right? So this is the transformation that you want. Does that make sense?
Yeah.
So now you said you want to evaluate at what? A. A is the first bit, right?
Yeah.
So you iterate over every bit string, right? And then you check for the one that has 1 at the beginning. So you will successfully find this, right? And you realize that the coefficient is 2, right? And you know the value you want to evaluate at, which is 3. So you will get the new result, which is 6, right? But then, how would you know where to put it?
So you change the index now.
Okay.
So if whenever you change.
You change which index? The
index of the value.
Or the value that you want to evaluate
the value
at.
that you have gotten, right? Becomes 1. When you apply A.
So A was 1, 0, right?
Yeah. So when you apply A, it becomes 0, 0.
So what it's saying now is that you flip. You know you are concerned with A right now, and A is the first bit, right? So you are checking for where A is equal to 1, and you found it. Then you took out that value, you multiplied it by the value you want to evaluate at, so you got 6. Now to know where to put it, all you need to do is just set A, that's the first bit, to 0. Do you get? So this now becomes what? And that's the constant. So you put it there. Does it make sense?
So if there's
Doesn't make sense at all.
So what if there's a constant 0? Is it okay to add?
So yes, so rather than just replacing, you add to whatever was there. Do you get? Who gets it? Okay. So that's like 1% of the class. Yes. Yes. So what they did was that you have a polynomial that has a set number of variables, right? The number of variables will determine the length of your bit string. So if you have 3 variables, you're going to be working with strings of length 3, right? So 0, 0, 0, 0, 0, 1. If you have 2 variables, you're going to be working with bit strings of length 2, right? So 0, 0, 0, 1, 1, 0. Then let's say AB, that's your polynomial. So A will take the first and B will take the second, right? So let's say you have AB, that will be 0, 0, 0, 1, 1, 0, 1, 1. Does this make sense? So with this, you can create that, right? So 0, 0 means that A was not present, B was not present. That's constant, right? Then 0, 1 means just B is present. That's why this one has coefficient of B. Then 1, 0 means A is present. And 1, 1 means AB is present. So any polynomial, any multilinear polynomial of 2 variables can be represented with this structure, right? All you need to do is just check the polynomial and put the appropriate coefficients there. So if you had something like 2ab plus 3b plus 4a, right? In the position of ab, which is this last one, you put what? You put 2. In the position of b, which is this one, you put 3. And in the position of a, you put 4. In this case, there's no constant, so that will be. So you can represent any polynomial of 2 variables, any multilinear polynomial of 2 variables with a structure like this. Does that make sense? So now that you have this, the main method that we want to perform on this is usually partial evaluation, right? So once you can perform partial evaluation, you can perform evaluation. So if you wanted to evaluate 3 variables, you can just partially evaluate the first one, the second one, and the third one. Does that make sense? Are you sure? Does it make sense? What part doesn't make sense? You want to skip dance? So
but we are doing this evaluation with the mind that we know what the equation is.
yes, kind of. Yes.
That means we know what the polynomial is. It's not like we are trying to interpolate or.
So you're not trying to interpolate. This is already the polynomial.
Yeah,
Like you just rewrote it in a way that you can manipulate, right? So you already have the polynomial in mind. Does that make sense?
Yeah. So if you are really like this, what if we have 2AB, 3BC, 4BD, stuff like that. So how do you now arrange it so that is it like A always takes priority such that, or the letters take priority according to their?
So now in that case, right? You said it's a 4-variable system, right? Right?
Yes.
It's a 4-variable system.
Yes.
A, B, C, D.
Yes.
So A will be the first, B will be the second, C will be the third, and D will be the. So if you have something like 0, 0, 0, 1, this is basically D.
D.
Yes. You can see the 1 at the end.
Oh yes, yes.
It matches D.
Yes,
Why the rest of them are 0?
Yes.
So this is D.
Yes.
Then also something like 0, 1, 0, 1. This is what?
This is
BD. Exactly. So if you enumerate the entire Boolean hypercube, there will be a corresponding 1 to each. So like the entire Boolean hypercube will be 0, 0, 0 up to 1, 1, 1, right?
Yes.
So regardless of the one you pick, you'll find a unique combination of A, B, C, D.
Yes, yes, yes.
So when you write your polynomial, you just figure out where does this belong to in this array, and then you just insert the coefficient there. So that's how you can represent it using that method. Does that make sense? You said? Hmm?
Is it that you arrange this A, B, C in the same way you arrange the one with two variables?
Yes. Yes. Not when I say it's the same way. I mean like you create a vector, right? And then the first one will be 0, 0, 0, 0, right? It's 4 variables now. Then 0, 0, 0, 1. Then 0, 0, 1, 0. Then 0, 0, 1, 1. On and on like that, right? Until you get to 1, 1, 1, 1. But then for each of these, there is a corresponding. Do you get what I mean now? So 0, 0, 0 means that A is not present, B is not present, C is not present, D is not present. So that means that's the constant. So this is const. This one, A is not present, B is not present, C is not present, but D is present. So this place will represent D. Then this one, that's C, right? And the other one is now what? CD. Exactly.
Does it?
So when you now have a polynomial, let's say 2ab, 2d plus 5cd, then the 2d will go, the 2 will go to where d is supposed to go, and then the cd will go to where 5 will go to where cd is supposed to go. You get? So this is how you write any polynomial of a 4-variable length. You guys should not think too much about it. This is not how we're actually going to implement stuff. But but just like for more context as to like how you could do it, yeah.
Yeah, I don't know. Can you go through the
Partial evaluation.
partial evaluation?
Yes, I'll do it now. Yes, I'll do it now. And then last question.
Yeah, yeah. Since it's not the one, but I wanted to ask like, so does it mean that for number of variables we have to now like map out, we have to create an array of this 0, 0, 0, 2, 1, 1, 1, 1.
There are way more efficient ways to do it. Yeah, there are way more efficient ways to do it. I'll also tell you guys another way to do dense. That's why I did it when I was implementing, because I didn't know about the other way. So I did dense. And there was a way I implemented it. So I'll tell you guys about that too.
And it did work.
Yeah, it worked. Oh, you don't believe dense can work. So yeah. Partial evaluate. Okay. So let's now take this polynomial that we have here, right? And let's partially evaluate it at so if we want to write this out, what will it look like?
Where's what up?
I think this is it, right?
Yes.
0, 3, 4, 2. Right?
Yeah.
So this is the same as that. And I also wanted to partially evaluate at a equals 3. Okay? So a is equal to 3. So what we do is we need to find where a is 1. You know, a is going to be the first bit, right? So this is going to be 0, 0. Yeah.
Go up it.
Okay. Or you want to look at this thing. This is constant. This is B. This is A. And this is AB, right? So AB is 2. B is 3. And that one is 4. Make sense? So now that we have this 0, 0, 0, 1, 1, 0, 1, 1, right? We're looking for the one that has A in it, right? That's the only one it makes sense to multiply the value of A with. So this one, does it have A? Because the first bit is not 1, right? Does this have A? Doesn't have either. What of this? So this does. So because this does, we're going to delete it, right? So we're going to change it to 0, but then we'll keep the value somewhere, right? Now we multiply it by what we want A to be, right? So that's what? 3. So the answer will be what? 12. Where are we putting this 12? So you know A was, we came to this 1, 0, right? And now we have evaluated A. So A does not exist there anymore. So we flip the bits. So it now becomes 0, 0. So we take this result, which is like 4 times 3, that's 12. And then we add it to 0, 0, which is here, right? So this now becomes what? 12. Does that make sense? We're here, right? So we go to the next one. Does this have A? It does. So we pull it out again. So this turns to what? 0. We keep the value. We multiply by what A is. This is the new answer. Where do we now put it? You know it was 1, 1. We have partially evaluated A. So it becomes what? 0, 1. So we have removed A from that. So we now go to where 0, 1 is, which is this. And then we add that result here, right? So that will be 3 plus 6, which is what? 9. So this means that we're done because we are the last one. So this represents the partial evaluation of that polynomial at A equals 3. I'm coming. Sorry. Let me just do the actual partial evaluation. But
so even though we partially evaluated A in that fourth index,
yeah.
Now, in the fourth index, that is 1, 1.
Yeah.
But there's a B also.
Yeah.
And now we are turning that value to 0.
Yeah.
If we are trying to partially evaluate B, B is not going to find that value.
That value does not. This place here represents what? AB, right?
Yes.
So if you had something that had AB before,
Yes.
and you partially evaluated it at A,
Yes.
you are not going to have AB anymore.
You are going to have B.
It's going to
Oh,
something
so that
B.
B will move
So that's why it
to
moved to
here.
B. Yeah.
Nice.
You get it? Did you get it?
Yeah.
Does anyone have a question? You know when they watch. You don't give up on them. So now let's evaluate it. Let's actually evaluate it. So 2AB plus 3B plus 4A, right? And we're evaluating it at A equals 3. So 2 times 3 times B plus what? 3B plus what? 4 times 3, right? So this is going to be 6B plus 3B plus 12, right? So this is going to be 9B plus 12. You see it? So constant is 12. Coefficient of B is 9. And remember, B was the second variable. You get? So it works. It works. Is it efficient? No. But it works. At all. But it works. Sparse is also not efficient. It's not more efficient, bro. So let me show you another way you could do this. I'll show you one more way. Then we'll go over to the way we're actually going to implement. Okay? So now imagine this. Imagine if you gave every variable a power of 2.
So is this the actual one?
No, this is not the actual one. This is still dense, but another way to do dense. Yeah, the one I did. Another one. So imagine if you gave every variable a power of 2. Okay? So let's say you had A, B, and C. Then A is going to be 2 to the power of 0. B is going to be 2 to the power of 1. And C is going to be 2 to the power of 2. Okay? So what does that mean? It means that A is 1, B is 2, and C is 4. Right? This represents the indexes of A, B, and C. Okay? So why I like this one was because of, if I wanted to know where A, B is, all I needed to do was just add, yeah. So the index is going to be at 3. That's my ordering. Okay? Okay. So we have 3 variables, right? A, B, C. We want to arrange them in an array. That's all the possible combinations of A and B, right? So constant A, B, C, AB, BC, AC, ABC, right? So what I did was that I gave each variable a number, right? I gave them a power of 2. So, or you can think of it as like, you just multiply the last one by 2, right? So you give this one 1, then you give the next one 1 times 2, and then you give the next one 2 times 2. Does that make sense? So A is 1, B is 2, and C is 4. Yeah. I don't know.
So,
I was just experimenting,
I think,
but there's a reason.
like,
I don't know.
it's almost as if you are following the sum of the Fibonacci's.
Not really.
Like, when you have 1 is 1, when you
Yeah.
have 1, 1, that is 2. When you have 1, 3, 1, that is
Yeah.
4.
Yeah.
When you have 1, 4, 1, 4, 6, 4, 1. That is, there's 2, like 2, yeah, Pascal, sorry.
Okay, Pascal. So there's a reason. Now that I'm thinking about it, I know what the reason is that this works. I didn't know that time, but I now know. But I don't want to go into that now. Okay? Let's just see how we construct the actual thing.
So it's possible to implement something and don't understand how it works.
Not like you know. Wait, there are different levels of understanding. So I understood level 1, but I didn't understand level 2. But level 2 was not necessary to implement. Yeah, so if it's 4 variables, if it's D now, that will be 8. So I'm just multiplying it by 2. So you want to see the
And let us understand the
4 variables? How many points? How many combinations are we going to have? 16. We'll do both. Okay, let's do 3 first. So now, constant is still at 0. That's fine. How many are we going to need here? 8, right? So this will be like 0, 1, 2, 3, 4, 5, 6, 7, right? So 0 is going to be the constant. 1 is what? 8. 2 is what? Then 4 is what? So this is how the initial variables are. Now this place is just what? 1 plus 2, right? That's AB, okay? So they go with their this thing. So 5 is what? AC, that's 1 plus 4, right? And 6 is what? And ABC.
Well,
So
I think this can get confusing. When you have an extra variable.
like D.
Yeah.
So let's do it now.
There are possible combinations.
Let's do it.
Three numbers.
Huh? 1 plus 2 is 3. 3 plus 4 is 7. 1 plus 2 is 3. And 3 plus 4 is 7. So like each position these are this. Every variable has a number, right?
Like we started. Okay, like now, what I'm asking is, when we are doing the rest variables, we're doing it like plus one. And what we got to say is like added the
No, yeah. So wait, are you seeing this?
yes.
This is directly A, right?
Yeah.
If you see anything that is compound that has more than one, you add the individual elements. So you can see AB now, right? A is 1 and B is 2. So when you add two of them, you're going to get what? 3. That's why AB is under 3. Then if you look at AC, A is what? 1. B is what? And C is what?
C is
4.
Sorry, C is 4.
Right? So AC is what?
So we are using the one.
Yeah. To sum. So ABC is now what? 1 plus 2 plus 4, which is 7. Yeah. Does that make sense?
Why is I'll get another.
No. You got ask her now. No. No, don't worry. What is the question?
Okay, like the thing, what I'm trying to say.
Yeah.
Since 7
Yeah.
is ABC.
Yes.
7 is ABC.
Yeah.
So 3.
Yeah.
Okay, C is 4.
Yes. Because it's there.
I'm trying to say, why didn't you just add ABC before?
ABC to 4.
Yes, now.
Why would we do that?
Since A is 1 and B is 2,
Uh-huh.
then okay, 4 is already C there.
Yeah.
Okay, now over for 5.
So 5 is AC, right?
Yeah, so why not do ABC? Because since A is 1, B is 2, 3 is.
So see. Don't confuse yourself, eh? Wait. The easier way to do this is to start with the possible combinations first. Then you insert them into the appropriate spots. Okay? So you start with what? A. And then you figure out where should I put A. A is 1, right? So for the singular variables, you know exactly where to put them. So B, this is going to be 1, this is going to be 2, and this is going to be 4, right? Then when you now start doing combinations, so let's say you do A, B. Then what you do is that you just add what A is and what B is. That's what? 1 plus 2. That's 3. So you're going to put AB at 3. Yeah. Then you do AC, 2, right? 1 plus 4, right?
Yeah, 1 plus 4, yeah.
That's what? 5.
That's 5,
What am I doing? Yeah, that's 5. Then you do BC, right? BC is what?
BC is. So why?
No, forget.
Why does C
What is B?
B?
Yes.
B is 2.
What is C?
C is 4.
So BC is what? 2 plus 4.
2 plus 4, that's 6.
That's how you know how.
So they're like looking at the future, so you're not calculating that. They are like you look at 6 for example.
No. You have already given A something, you have given B something, and you have given C something. So whenever you see anything that combines them, you just use those things that you have given A, B, and C to know where to put that thing. Does that make sense?
Then for 7 is
So then ABC, what is A?
A is 1,
What is B?
2,
What is C?
4.
So when you add everything, 7. That's why ABC is at 7.
So if you were to do an 8, how would you do?
There's no 8 because of we're using 3 variables. And because we're using 3 variables, the highest 0 indexed is 7. Yes. Does it make sense?
Yeah.
So now what to do for ABCD? Okay. Yes. 2 to the. Huh? Yeah. Yes. So 2 to the number of variables will tell you the length of the array.
How the ABC 1 to 4, we're adding to or raising to power?
By adding 1 plus 2 plus 4.
No, I mean like how you got A to 1, B to 2, and then C
Oh.
to 4.
Yeah, so it's like there are different ways you could do it. You could always put the first one as 1, then any consecutive one you just multiply by 2. Right? So 1, then 1 times 2 is 2, then 2 times 2 is 4. or you could do powers of 2. So the first one is 2 to the 0, 2 to the 1, and 2 to the 2. Depends on the one that makes most sense to you. But both of them are equivalent. Does it make sense?
I think this I think what I raised earlier. So if I raised earlier it's not an issue because I think there is no repetition.
Yeah.
And then permutation is like
It's powers of 2.
yeah.
I don't know how to put it. Like 2 to the 0 is just what? It's just 1. Then 2 to the 1 in binary is 1 0. And 2 to the 2 is 1 0 0. So regardless of how you add them, it's always fine. I don't know how to explain it.
As long as there's no repetition.
As long as there's no what do you mean repetition?
Like 1 0 0 is not 0 0. Like
No, it's not. Because of A is depending on the position, you will have different powers. But let me know. I didn't want to go into this because this is quite confusing. Yeah,
So that means if we had a D,
we'll do that now.
that would be
Yes.
16.
No, that would be 8. No, you're talking about what D will be up here, right?
Yes.
It's 8. It's just 4 times 2.
Okay, just times 2.
Yes. So just times 2. Or 2 to the power of 3, depending on how you want to do it.
Is it like a law? Is it like a law that says
It's just me that feels like that. Something about numbers that you can do that, yeah.
Okay, so that means in this case now, if you are doing any evaluation, you are basically just minusing the power of that.
They jump, but yes. Yeah. You have gotten partial evaluation, yeah. Huh? We'll go over that. It went forward. So you have seen the future already. Yeah.
So the reason why you're using these because of what you're
With the binary. Yeah. You can always combine them and you can always know what makes what up here. Does it make sense? Should we proceed? So let's do for A, B, C, D. Okay? So now A, B, C, D. What we'll do is that we start with A. A is what? B is what? C is what? D is what? So these are things that we'll use. Then all we need to do is just write out all the other ones. Okay? So that's what? I think AB, AC, AD, BC, BD. See, this is what you wanted us to do. ABC, ABD. What else? Eh? ACD, Okay, let's do it the other way. This is 2.
Yes, let's just start with C.
How many elements are we going to have? 16, but 0 to 15, right? So let's do this. So this will be what? 0, 1, 2. Right? So this is what? Constant, right?
14, 15. It looks like 16.
Are we following? Yeah. So 0 is what? Constant, right?
Yes.
What is 1?
A.
What is 2?
B.
What is 3?
AB.
Relax, yeah. So 3 now is going to be 1 plus 2. So for any value, there's only one combination that can sum up to that value. So for 3 is what? AB, right? What is 4? What is 5?
It's
Called 1 plus 4, right? What is 6? What is 7? What's 8? 8 is D. It was already a given. What's 9? What's 10? What's 11? A what? What's 12?
CD.
Yeah. 8 plus 4, 12. What's 13? You said? Yeah. 3 and what? It has to be one of this. If it's not one of them, you don't use it. You get? So what's 13? What is 14? Right? Then what is 15? Does it make sense? So all we have been able to like represent the entire thing as in a dense form with a standard. That one, the other one also works, right? It also works. All of them are inefficient, so it's still fine. But this one is just the one I implemented, and I really like this method. Yeah. Which one? No, this one we scrapped this. Oh, you mean this ABCD? This one? No, we scrapped this one. It was too confusing. So what we just did was that we just wrote the numbers, and then we figured out what you need to add to get them. Yeah. So let me show you what this thing looks like. So A now, right? A is like 3. If you are doing, that's 4 variables, right? Yes. A, if you look at 1 is actually this. 1, 2, 3. This is A in binary. Then look at B in binary is this. If you look at C in binary is this. And look at D in binary is this. So it's doing what we were doing, but with numbers. So AB is just B and A. So A is like the last position in this case. Then this is B, then this is C, then this is D. So AB is just turn on A and B. That's what happens when we add. It becomes 0, 0, 1, 1. So this AB is what? 0, 0, 1, 1. And 0, 0, 1, 1 is what? 3. And if you look at 3, you see AB. I don't get it. I don't know how. That would be like a proof, right? You are trying to say that there's no. What if, like, you're looking at a bigger space right now, right? And then you have an index. And you're saying that there are 2 ways to get that index from the same.
There can't be 2 ways.
So do you have an intuitive proof for why they can't?
The intuition is that since one letter cannot be repeated twice in a particular index, there can't be.
I think.
Yeah, but that's not enough of an intuition.
It looks like a 4x4 matrix mapping, so that this is ABCD and
Continue.
this ABCD.
Don't mind them.
So at the end of the day, even if you have A to J and A to J here, like there's no way that you are going to have, like, even if you have an 8x8 matrix system, there's no way like any of those two.
I know.
Any clash between.
I know. I know. Wait, sorry. I know what. Okay, let me see. Let me hear what you want to say.
The problem is, the solution is, do you know what we are doing here is in binary? Yes. I know that it's just the base we are considering. We are raising the base to the power of the variable we are in. That is why it's two of them are the same. It's just that we are writing the same thing in different ways. What he has done and what we did yesterday are the same thing. This thing is just conversion.
So okay, yes, continue.
We converted what we did yesterday and we work perfectly. So they won't believe if what we did yesterday.
There's another. I'll figure out.
Then this one will be full because they are the same.
So see.
Since our own will not fail, it's going
Okay, wait, see. See this. That's prophetic proof. Okay. Oh yeah, wait. So see. Look at this. Look at it this way. Every decimal number has just one binary representation. Do you get? So 2 can only be represented one way in binary. Wait. 2 can only be represented one way in binary, right? Which is like 0, 1, 0, right? And 8 or 100 or 1 million only has one unique binary representation. Okay? So if we have a random binary representation like 1101, right? If we're trying to get this from nothing, we need to somehow bring 1. That's like, this is like 1000 plus 0100 plus 0001, right? And these are so all these things, right, they have just one bit in them. None of them is ever going to have 2 bits. Do you get? So the only way to get something like this from things that have just 1 bit is only one way. I don't know if that makes sense. You're getting me a bit, right? Every single one of them is only going to have 1. The rest of it is always going to be 0. Then if you look at any number, it's built up of certain ones, right? So what you need to add are the ones of that, right? So you just take like, this has 3 ones inside. That means that you're going to add 3 numbers. And those 3 numbers have to have ones in the correct places. And there's only one way to do this. Like, you cannot add things that have just 1 other than those 3 to get this back. This is why you always have one unique summation. This is just a sketch. Yeah.
I think again what she's trying to say is like it's possible when you add
Yeah.
get like the same values, like 3 plus 1
And
is equal to
2 plus 4, yes.
But the problem is you never get 2 plus 2 because you can't have like
Yeah, but that's not sufficient, right?
No, our argument is contradiction to prove
Yeah.
right? So if we can only find, we don't need to prove everything. We can only find one negative, then it proves 0. That's like a contradictory argument. So if we can prove, like for instance, if you say your statement is like there exists something. So if you want to prove your statement, you can say, if you want to prove your statement, you can just find one that is not. So it proves yours.
Wait, wait. This proof requires a for all.
Yes. So
Yes.
if you want to prove your statement, we can just find one.
One what?
One anomaly.
But you can't because it's making use of powers of 2. And the powers of 2 only have one singular
I think
place.
that's just the best way.
Powers of 2 only have
So,
one.
but she's using it from a decimal.
You understand? Wait. Yeah.
Just like randomly connect one binary number to
Yes, like put one in 7 places. You still only have one.
Yes.
If you're breaking it down, it's 2.
So you know, like ABCD, right? ABCD is what? 1, 1, 1, 1, right? Right? If you wanted to get the single bit decomposition of this, right? That would be what? 1, 0, 0, 0 plus what? 0, 1, 0, 0 plus 0, 0, 1, 0 plus 0, 0, 0, 1. This is what? A, B, C, D. That's why this is A, B, C, D. Does it make sense?
So instead of adding that, you could have just added A here at the bottom, which is still give us.
No, we'll give it 2. Yeah, exactly.
Sorry. I think you write everything out. Like, these words.
Is there?
These words. No, like, on the.
If you add
This is that level 2 understanding that I skipped. Wait. I'm coming. I want to talk about something. You are trying to prove something, right? Like you are trying to prove that something holds for all cases of. Then, so to prove that, you can prove that by proving for all, and you can prove that it doesn't hold by finding an anomaly. So, but you can't prove that it works by finding just one case that it works. Yes. So what were you saying? So what were you saying about the anomaly and the proving for all?
I was trying to prove by contradiction.
Okay.
That let's assume your statement is wrong.
Okay.
That means there will not be
There will be a contradiction at some point.
Exactly.
But then when you're talking in that sense, you now have to talk in like a general sense, right? Like when you're proving by contradiction, you have to talk in a general sense.
That in fact it works for all.
Yeah. Something like that. But no. Okay, are we good? Do we understand how to represent it? Who doesn't understand? There are multiple ways, but I've looked at 2 today already. Who doesn't understand? Okay, I'm assuming we all understand. So now that we understand, how can we now do... I'm not going to put so much energy into this, so we want to move over to the next one. But then how do we, let's say, partially evaluate this now? So when we want to partially evaluate, we'll say a variable name, right? And the value, right? So what we need to do is just find where that variable exists. Then how do we know where to put the result? We just subtract the... So let's say we wanted to evaluate at A, right? So we come here. A is what? A is 1. So we evaluate A here, and then we now do this index minus 1. That's where we're going to put the answer. So the answer is going to be...
Sorry. Come on, that belly.
I'm going to come again. I'm glad I didn't understand what you're saying. So we're looking for all the places that has A, right?
Yeah.
That's here, and here, right?
Yeah.
Here, and here, right? If we evaluate ABC at A, what will be the new variable? BC, right? A will disappear. What is BC? 6. A is what? 1, right? So 7 minus 1 is what? Do you get? It moves to BC. Let's try for the other one. AC. That's 5, right? If we subtract 1 from it, that's what? 4. Is that where C is? Do you get? Then what's AB? 3. 3 minus 1? That's where B is. So it's always telling you where. And if you want to evaluate multiple things at once, so let's say I wanted to evaluate AB, you can just subtract the sum of AB from it. Do you get? So let's say you wanted to evaluate AB. A is what? 1, and B is what? 2. So we're subtracting what? 3. So 7 minus 3 is what? That's AB. You get? So you can do this kind of like manipulation. Does it make sense?
Yeah.
We're not implementing this.
So how does the value move back to?
It moves back. It moves to where. Okay. So let's say I'm evaluating AB, right? But I'm evaluating just A, right? So I'll take the coefficient of AB. Then I'll do my multiplication with what I'm evaluating, right? So I have my new coefficient. But I'll put it at 3 minus A. I know A is 1. So I'll put it at 2, which is where it's supposed to be. But when you evaluate this at A, you have just B. Do you understand?
Sorry.
That's an example. Or you still want me to just explain?
Yeah, come again.
Okay. So AB is here, right?
Yeah.
When you evaluate AB at A, the answer is supposed to go where? To B. So there's no more A. Does that make sense?
The answer is supposed to be at B.
Yes. So let's say you had something like 2AB, right? And then you evaluated A equals to 3. That will be what?
6B.
So the coefficient goes to B.
Okay.
It's no longer in that AB cell.
Yeah.
Does that make sense?
Okay, yeah.
So every time you evaluate, you move the coefficient from the cell it was to the cell it's supposed to be. Does that make sense? So it was at what? AB.
Yeah.
Then we did the evaluation. We got that 6. So to know where it's going to go to, we just subtract what we evaluated from the current index.
So I'm getting the mathematical explanation. So the picture I'm playing in my head is like, okay, if you want to represent this now, like,
In code.
Is it that, yeah, in code. Is it that we have like 2 arrays?
No, 1 array.
1 array.
Yeah. Let me show code. So look at this code now, eh? See how long it is. This is multilinear polynomial. And all of this is not useful. Like, compared to this one we're about to teach you, it is crazily smaller than this and way more efficient. Now test. So test stopped, test started here. So like 500 and something lines. So initially I had like, so this is what I was saying, I was doing dense sparse. So normally you're supposed to have like a vec of all possible combinations, right? And then have zeros there. So what I just did was that anywhere that there's supposed to be a coefficient of 0, I just don't put it there. But I want to go back to the I don't know if I can even get that history. I'm not sure I can get that history, to be honest. What would be the easiest way to do this, man? So yeah, I was using vec of f. Alright. If you look there, instead of bit map, I'm using vec of f. So this was the original implementation. Then there's now, let me check for partial evaluate. Why did I do interpolate? Okay, I did interpolate. Yeah, that's true. I didn't even do this. So we'll just use the regular one and then we'll just see. But you can just assume that it's a vec of f. Okay, yeah, so I'm not going to explain the entire code. It's just too much. But what did I even do here? What was this? Yeah, sure. Is it better? So this U size here is the index, right? Are you good? Can you see it? Or the light?
Yeah,
I can't do anything about it. You can't see. Is it that it's too small? Or because of the light? The area of light. Is there light mode for...
I'm the one that has
So this U size here, right? The U size is the index. U size is the index, and F is the coefficient. So if I wanted to put ABC, let's say it was 3ABC, right? Then I'll do A plus B plus C, right? That's 7. So 7 will be the U size, right? And then the coefficient, which is 3, will be here. So that's just, it's still the same, but I did not want to waste space in terms of like putting zeros everywhere. Does that make sense?
That's like sparse.
It's like sparse, exactly. But with, instead of putting a tuple, I'm putting the sum of A, B, C. And then I'm using that as the this thing. So it's like sparse, essentially. So let me look at partial evaluate. So this partial evaluate now. Let's just come here. This is where we really care about. So what I do is that you are setting me to evaluate at a particular index, right? So let's say AB, right? So AB is going to be at position 3, right? So this I here is 3, okay? So what I do is that I remove that old coefficient that was at 3. You delete it from that spot, right? So that's why I call this old coefficient. Then I now get to the place I'm supposed to put the result. So the way I get that is I just do I minus, so I have something that can convert every variable to the corresponding number, right? So this will now be like I minus 1, because A is 1, right? Which will now be like 3 minus 1, which is 2. So it means I'm going to put the result at position 2. Then I'll now do this, I update the coefficients, right? So I just multiply the old coefficients with the thing I'm evaluating A at. So I now get the new coefficient. So once I get the new coefficient, I now insert it into the polynomial. So this is how you can just like insert it into the Bitry map. So it's not difficult. The rest of this is just like, and it's to give you like 1, 2, or 4. Not in a string, in position. So like A is 0, B is 1, and C is 3. Or 4. So it makes it like it's just raising it to the power of this thing. Does it make sense? Any string. You can't. But strings are less efficient. Eh? I'm coming. Yeah. Bitry map. It's like a map from some key to some value. So if you call it with the key, it will give you the value.
Sorry?
Yeah.
You write this all together.
No, you're not doing this code though. We're doing another method for multilinear polynomial. This one is just for context.
Yeah.
As to the history.
Yeah.
But this is not what you're doing. What you're doing is shorter but harder. Slightly. Like harder to grasp. Does it make sense? So what I'm thinking now is that you guys should go and eat. Then when you eat, you come back and we now do multilinear. Yeah. Huh? Come on, sir. So we'll come back by 11:15. 11:15. 30 minutes is enough. And we have a long way to go.